All right. In 6.2, we start looking at a new use for integration. One way to think about integration, at least based on what we've been using it for, finding areas under curves, is integration is a way to add up an infinite number of infinitesimally small things. Basically, what we were doing, if you remember, as we were finding areas under the curves, we started off by covering the area that we wanted by really narrow rectangles. And we got an approximation. And then if we added more, even narrower rectangles, and added up all of their respective areas, then we got a better approximation. And so the whole process was to let the number of rectangles go to infinity. And of course, as they went to infinity, they got skinnier and skinnier. So what we were ending up doing in the integration process is adding up an infinite number of infinitely skinny rectangles, areas, and that became the area under the curve. Well, we can extend this same idea to solids, and so a three-dimensional object. So, like the one you have in a picture in the picture here it's a pyramid, a square-based pyramid, and it's laying on its side. That's kind of an odd orientation, but we do it that way so that we can start thinking about functions and things like that. If we were to look at this, even with from the side, without the three-dimensional representation, this pyramid would look something like this. All right, and it goes out here a distance a. All right, let's say let's have it go out here a distance say out to 10. All right, so its height is 10, and it's got a square base, and let's say that base is, well, let's make it 10 as well. So that makes this 5 and this 5. All right. But that's the sideways view of this rectangle, kind of boiled down to a two-dimensional object. Now, the idea is there are lots of objects that we can do this with. The ones we're going to start off with are fairly simple, and they're simple in this fact that if I were to take and imagine this was like a loaf of bread, and I were to slice out a slice from that. So imagine going over here a distance x and slicing out a slice of this pyramidal shaped loaf of bread. What I'm going to get is a shape that looks like this, basically. It's a square, okay? It's a square. Well, we'll write it like this. So it's a square, and it's the edges are not exactly 90 degrees, right? So it's going to look something like that, right? But here's the thing. If I cut it thin enough, right? So if I cut it so thin, basically I can treat it as if I don't have to worry about that little bit of angle right there. I can just pretend that that's a straight across, because that's essentially what I'm doing. So the idea is if I cut it, I get a square, right? I get a square. It's actually a really thin slab, but it is square shaped. All right. And it doesn't matter where I cut, I still get that square. It might be bigger, but it's still a square. All right. So this is the first kind of solid we're going to be able to find a volume of. Is the kind of solid where if you slice it, you get an identifiable shape. And then if you slice it a little way, farther into it or farther along the x-axis, you get the same shape, but it might be bigger. So in other words, you get a square and a square and a square. They might be bigger. Or you might get circles, or you might get semicircles. But each time you slice it, you get the same shape. All right? And so the idea is I can find the volume of that shape because it's just a square box or a rectangular box with a square side, right? I can find the volume of that shape because it's just length times base times width, the product of the three dimensions, right? And that's why it's important that I can ignore these kind of, the fact that I'm not straight across, because the reason I can do that is because I'm taking this slice infinitesimally thin. So essentially, I am good. It's kind of like we did up here, right? I just I just made my rectangles straight across so that I could calculate the area. So that's what I'm doing here. So what I need to do is I need to find the volume of this slice. Now this slice came from this location. I went over a distance x and I took my slice. All right. Now let's add one other piece. And the piece we need is we need to know what the equation of this line is right here, right? And this is why we put it on an xy axis so that we could use the equation. That equation is going to be important because I need this dimension, which is right there. All right. So if I look at that equation, it goes through that line. It goes through y equals 0, 0. And it has a slope of over 10 up 5. So it has a slope of 1/2. So the equation of that line is y equals 1/2 x. And that equation can be used to find any point on this curve. So, in particular, I need this because that is this dimension. All right. So if I go over a distance x, right, like I did in my picture here, then if I plug x into the function, I get 1/2 x. The height, this distance is 1/2 x, so this total distance is just x. So in this particular case, the measurement here is x. This box, this slice that we took out, has a height of x. All right? Now, because it's a rectangle, or because it's a square, it actually turns out to be x by x. Okay, so that's nice. Now, the other thing that we're going to do here is when we make this slice, we're going to call that thickness dx. It's just a little tiny bit of x. That's kind of what the dx stands for. And so if I use that fact, then I have my third dimension of my slice as dx. Okay? So the volume of this slice that I've been working on can be found simply by multiplying the three dimensions. So I have x times dx, or that is the volume. Now I call that dv because I'm going to use v to represent the entire volume of my entire shape. dv will represent one little slice of that volume. So dv equals that, or more precisely, dv equals x squared dx. So that is the volume of one slice. Now here is the beauty and the power of integration. If I integrate all of those little slices, in other words, if I add up all of the volumes of those little slices using integration, I get the volume of the whole thing. That's a powerful result. So now, the other thing we need to add is we need some limits of integration. I start making my slices here, and I stop making my slices here. So that if I say it that way because that tells me I start making my slices at 0, I stop making my slices at 10. And that's the integral. If I can evaluate that integral, then I will have the volume of the solid. And it looks to me like we get what? 1,000 over 3 minus 0, minus 0, or 1,000 over 3 is the volume, and say this is inches cubed. All right? So this little approach works if we're dealing with shapes that we can slice and always get the same shape, maybe bigger sizes. And the other thing about that is the shape we get needs to be a recognizable shape that we can find volumes of. At this point, we're stuck with the old traditional volumes of boxes. We can do that. We can find volumes of triangular objects, right? Of triangular objects. We can find even volumes of semicircular objects. Sorry, that's a poor rendition. But semicircular objects, just because it's the area of the side times the thickness, all right, for those kinds of things. All right, so practice, that's an introduction to finding volumes of solids of uniform cross section is what we refer to that as.